Thank you everyone for showing up today. It's a great honor to be at this stage of my career. So today we'll be talking about robot learning and deformable manipulation using simulated interaction, architectural priors, and curricula. So here's how the talk will be structured. So we'll have some introduction, motivation, prior work. Then most of the talk will consist of a series of 3 perspectives on how we might approach robot learning and robot manipulation, including simulated interaction for fabric manipulation, network architecture for rearrangement, and curricula for accelerated learning. We'll then discuss some ongoing and future work ideas, followed by a fun section at the end where I acknowledge and thank a variety of people who helped me along the way. So there has been a significant amount of recent progress in robot learning for manipulation with applications like bin picking, tossing, and reorienting a cube. While these results have been very impressive, what's key here is that there's a learning involved, so that given some training data, the robot is able to learn something and then hopefully it will generalize to new objects. But what these approaches often do, they make explicit or implicit assumptions that these items are rigid items or they're almost rigid, in contrast to highly deformable items. But highly deformable manipulation is a very interesting task because it involves areas like manipulating laundry, bed making, and wrapping items. But in contrast to rigid object manipulation, deformable object manipulation has several challenges. So some that I like to highlight here are, number one, it's difficult to represent the state of an object, or basically where it is. Because if you think of a rigid block, then if we know a specific point on it and its position and orientation, then that tells us where the block is arranged in 3-dimensional space. But in contrast, if we have like a flag, for example, we might know if we know the specific point of like one point on the flag where it is, the other point could vary a lot. In addition, when robots are gripping deformable, often they're gripping something, but they really want to control like every part of the deformable, including items that are far away from the gripper. And on top of this, there's also difficulty in designing a policy where there's complex dynamics. So like given an action, it's not clear, what's the state going to look like after the action is applied. So in this talk, we'll discuss different ways to potentially address these challenges using machine learning. There's been a lot of prior work in manipulating deformables, including tying and untying knots, folding towels and laundry, and smoothing slightly wrinkled fabric. One thing I like to highlight about the prior work is that around 2010 or so, the dominant approach was roughly for fabric manipulation, run a traditional computer vision algorithm like corner detection or edge detection to determine the state of the fabric. Then we could define a geometric controller on top of that, like gripping the lowest hanging corner of the fabric. Over the last few years, the robotics community has adopted many of the end-to-end deep learning techniques that have become pervasive throughout modern AI. And as one of the first steps in this process for deformable manipulation, we worked on a paper for robot bed making where we train a deep neural network end-to-end from high-dimensional depth images to determine the corner of the blanket where the robot picks. So that work served as a good prologue toward what to come next when we discuss simulated interaction for fabric manipulation. So here's the problem statement. We'll have the goal of flattening fabrics from the highly rumpled, wrinkled configuration. Our goal is to take a data-driven approach. So for that, we want a simulator so that we can get a lot of data fast and in simulation. For this work, we developed our own fabric simulator. for several reasons. So the number one, existing fabric simulators were either, they were either under development concurrently with our work, so we didn't know we could use them, or the simulators were also very high fidelity, which means they're very accurate in terms of physics, but that also means that they might be very slow. And we need a trade-off between something that's just accurate enough, but it's also fast enough that we can get a lot of data. So here the fabric is a 25 by 25 grid of vertices with the underlying state, and then the image is generated from the top-down image, and the goal is to maximize coverage over this background. So in order to do this, the robot had to take action. So we're going to parameterize action based on a sequence of pick and place action. So this means each action consists of a two-dimensional coordinate for the picking point, followed by a pole vector for the placing point. And we'll use a fixed height delta when we're picking and placing. So that just means we pick at a point, we'll lift by a certain amount, drag it across the plane parallel at that height, and then we release. So that's the action. To actually train the policy, we use deep imitation learning with Dagger to train the policy. So Dagger is a very effective technique widely used for imitation learning that assumes the presence of a supervisor, which can provide corrective label telling the robot what it should have done when it was at those states. So here, the Dagger supervisor is algorithmic. It performs corner pulling. And here, an example episode is shown below, where there's color images on the top, there are depth images on the bottom, and the actions are overlaid with the pick and place arrows. And the supervisor just does the bipartite matching between corners of the fabric and corners of the plane, and then corrects for the largest discrepancy, so that in this example, it goes from 38.4% coverage to 95.5% at the end. Okay, so that's the supervisor. The ultimate goal, however, is to transfer it to a physical robot. So when we train in simulation, we use domain randomization. So that's a very effective technique for sim-to-real transfer. It involves, in our case, randomizing color and camera angle so that the real world looks just like another variation of simulation parameters. And then we deploy it on a physical Da Vinci surgical robot, with the long-term goal being, if we can get the policy to work reliably, maybe we can get surgical robots that can smooth patient clothing and gauze and so on. For physical experiments, we compare coverage performance using first 3 different difficulty tiers. So we have 3 different difficulty tiers of starting configuration, followed by 3 input modalities. So we have color, depth, and the combination of the 2. And what I want to highlight with the results here is that the RGBD policy with the depth will attain the highest final coverage on the harder starting configuration, like the one that on the harder starting configuration, because of the increased, more pronounced wrinkle in those states. Okay, so here's an example of the policy in action trained entirely in simulation, where the color and the depth images to the upper left show what the actual input. And if you look at the corners, they're not totally exposed. Like the fabric corners are partially hidden in many of these time steps, but even so, with pick and place that roughly the corner region is able to get enough coverage to end the episode. All right, so that was good. We have a fabric smoothing policy, but there's some red flags here. So 2 obvious ones are, we trained a smoothing specialist, so we're going to have to retrain for folding and other tasks. Number 2, it requires implementing an algorithmic supervisor. And we could do that, but maybe that's harder for other tasks, and maybe it doesn't cover all the starting configurations that we want to consider. So the question that we pose here is, can we have a more general fabric manipulation policy for arbitrary goal images that show the desired configuration. So we propose VisuoSpatial Foresight in this paper, which involved training a dynamics model on simulated data using the same simulator we developed in the prior paper. And then we can develop a planner on top of that. So we're going to first discuss both of the components right now. All right, so the first major step of VSF is the dynamics model. This is also referred to as the video prediction model. So basically, it learned to map, or we have some current observation and a candidate action sequence to take, and we want to predict what are the resulting observations. So the research community has developed a variety of video prediction models, including Stochastic Variational Video Prediction and Stochastic Video Generation. So what I want to highlight with this equation here is that this is a generative model that shows the probability of sampling a specific sequence of future frames from the current time step into the future while we're conditioning on the candidate action sequence of H actions, and we have context images as well. Those are images from the prior time step up to the current one. And the factorization will result in some draws of a latent variable, where each draw of a latent variable will produce different plausible futures, which is important because the context images might not contain enough information to convey all the physics properties of the simulation. All right, so that was the generative model. Here are the predictions in action. So here are some qualitative results. The top row shows the true color and the depth images, and on the left and the right, they represent the same fabric. I'm just splitting them up for readability. So this is from the data that we have. The policy that we use to generate all this data is basically a random action policy because we didn't want to embed any task-specific assumption. So from this, we have the two video prediction models, SV2P and SVG. Those video prediction models have to, when they're given the images in the context images, in the blue boxes, along with 5 actions in the future, they have to predict what are the predicted images going to look like. And we see that even though the predictions tend to get blurrier as time goes on, they still roughly predict that the fabric moves to the top region. So these qualitative results, along with other quantitative results that we explored, suggested that the model might be accurate enough for planning. And that's the second major step of VSF. So here, the planner is what decides what action they'll be taking. This is implemented with the cross-entropy method, which is a sampling-based algorithm for optimizing an objective in a derivative-free fashion. So in our case, the thing that we're sampling are action sequences. Each row in the image here represents a sampled action sequence, along with the predicted images from the video dynamics model from the prior slide. So we will rank the action sequences according to a cost function based on the Euclidean distance towards the goal image. And then after doing that, we can refit a multivariate Gaussian to the top few sequences. We'll resample, and then we repeat the process. So that will ultimately it will give us a best sample sequence of 5 actions in our case. We take the first action in the sequence, throw away the rest, and then we'll repeat, since that's model predictive control. So this is how the policy works. And here are some examples of it in action, where we have the rollout on the left. And even though the policy has been trained on smoothing specific data, it does a pretty good job. Here are a single triangular fold. And in this case, it's able to do the job in roughly 2 actions. And it can't do it in 1 action. And the reason is we limited the action magnitude in training because a larger action magnitude might result in on average, larger pixel changes due to greater variation than the clock change. So that hindered training. So we limited the magnitude, and that's what we get. And finally, the most interesting case here happened with the double fold here. And if you look carefully at the goal image, it shows the lower left fabric corner above the upper right corner. And the same thing happened with the actual rollout. And this is something that the depth modality might help us out with, because when you use the depth modality and the cost function, and it's useful to tell like which layer is above another one. All right, so good news, VSF is able to do smoothing almost as good as an imitation learning agent that's specialized to the task. However, in the first version of the paper we didn't get the physical folding to work that well. And the reason is we had some compounding approximation errors during the sim to real process. So in an extended version, we tried to explore every way that we could improve the VSF algorithm. And the things that resulted in better folding in the physical world were just slightly increasing the length of the action magnitude a little more, and like changing some of the base colors and the actual fabric that we tested for the physical experiment. And the result is something like this with the surgical robot. So it's the same surgical robot from the prior paper, and it's able to do a 2-action episode to fold the fabric to the upper left triangular fold. All right, so that's a discussion of how we use simulated interaction. And in this next paper, we're going to take a slightly different perspective and discuss benchmarking, and also why I really like neural network architecture design. So for this project, we have 2 main contributions. So the first is a suite of 12 simulated tasks in PyBullet that span a wide range of deformables, including cables, fabrics, and bags. And there are multiple reasons why we did this, but the biggest one I think was we wanted to accelerate progress in deformable object manipulation. So we provided this benchmark for other researchers to use. The second main contribution of this work is a set of model architectures for manipulating objects toward desired goal configuration, specified with images. So again, it's pretty similar to the prior paper where a separate image specifies the desired object configuration. So again, we'll discuss all these in detail right now. So first, about the benchmark. In the simulated benchmark, all the tasks that we have involve a simulated UR5 robot arm with a workspace in front of it. And there are some objects that it has to manipulate, and a success criteria for a task can be defined in multiple ways. So one way is by designing some green anchors on the workspace that show where the cable should be manipulated toward. Other tasks are goal conditions, like the one shown here where there's a separate input image from the top-down camera view that's passed in as input, which is paired with the starting configuration, and that specifies what a success means. I also want to highlight that each task has its own demonstrator, a scripted demonstrator, because we are going to use it for imitation learning. We also have tasks that involve fabric, like in the prior paper. So these include tasks like wrapping and smoothing items towards target zone. Either they're on the surface, on the workspace, or they're specified with an image, a separate image. Finally, we have the most interesting case, which is with bags. And robots that manipulate bags have a very obvious application, because this would enable robots to transport many items simultaneously rather than try to do them all one by one. But before this work, we've seen very little prior work in robot and bag manipulation, because there are obvious complexities in simulating bags and manipulating bags in the real world. So what we did for this is we took a sphere mesh, we moved it in PyBullet, and then we removed some vertices at the top and attached a series of rigid bead at the bagged opening to try to simulate drawstring style bagging behavior. And that helped a lot to stabilize the physics. So the task with bags involved opening the bag, putting in 1 or 2 items in it, and either moving that bag to a target zone or putting in the goal condition case, if the bag is in one of the 2 items, the robot has to put the item in the appropriate bag. So that's the yellow one in this case instead of the blue distractor bag. Okay, so that's the set of benchmarks that we propose. But now we have to decide, what are we going to do to try to train policies that can, reasonably try to manipulate the benchmark. So that's where the neural network architecture approach comes in. So the architecture that we use is based on something called transporter network, a recent innovation presented at Coral last year. So first, let's review what normal transporter networks does, and then we'll review what we did. So transporter networks are neural network architecture. They're very well suited for picking and placing and, in general, rearranging visual input. The first major step is to localize a region of interest. And then next, we have to infer its spatial displacement. The localized region can be centered at some picking point that the robot picks at. It can encompass the entire object, part of the object, or multiple objects. One way that we might be able to implement the spatial displacement is by defining 2 continuous control values, delta x and delta y. Transporter network does not do this. Instead, what it does is it directly takes visual features and directly does a brute force sliding search across all the possible placing displacement points. This is conceptually the same thing that a convolution operator does in 2 dimensions. So if you imagine a 2D convolutional neural network with a wave filter, it does the same sliding kind of motion on a 2-dimensional image. So we can efficiently implement this on a GPU. And the result is that in the correlation map, the highest value, the highest pixel value, indicates the displacement point. All right, so one more higher level overview of transporter networks. So the transporting operation happened near the end, where I want to highlight here that the transporting the original image and the crop images, they're not directly used in the transport operation. We first have to pass them through fully convolutional neural networks, and then to get featured before the features are then used for the transport operation. So fully convolutional neural network, in this case, they're residual network with 43 layers. They take in some image, and then they produce an output image of the same dimension, but where the image is not really meant to be an image that we would interpret very easily. They're meant to be features. Last thing I want to highlight here is that we're using orthographic images, and then that means there's a lot of equivariance here. And this is very helpful with training transporter networks because it facilitates data augmentation. So if we translate an image by some amount, the picking and the placing label, which come from demonstration, should also translate by the same amount. So in practice, that improves training. All right, so here's what we did in our work. We brought the goal conditioning into transporter networks. So we're going to go through the forward path of this architecture carefully. And as before, we have a current image, and we pass it through 3 networks. All these networks are, again, they're fully convolutional neural networks. So they produce some features of the same size as the input. In here, we also refer to them as logic. So logic and features mean the same thing for our purposes. There is also a picking network, which produces a heat map, where the higher values indicate the more likely picking point. So that's good, but now we have to use the goal image information somehow. We're going to do that by taking the goal image. And number one, we're going to pass it through the picking network again. So the picking network will take both the current image and the goal into account. But we're also going to pass it into its own goal image to produce in its own goal network so that it produces features for that. Okay, so at this point, we have a bunch of features. Now, before we can apply a transport operation, we have to somehow use the information from the goal image. Otherwise, we're not taking advantage of that information. So the way we do this is very simple. We do some element-wide multiplication with the goal times the query logic and the goal times key logic. So query and key are just terms that we take from the databases community, and we name the networks that way. The result is that we get two sets of features, goal times query and goal times key, that both utilize goal information. So now the goal image information should be propagated there, and therefore we can proceed with a normal transport operation by taking a crop centered at a picking point and then doing the same brute force convolution search, resulting in a heat map for placing where the highest score indicates the placing spot. So this can all be learned end-to-end through backpropagation from demonstration, where the demonstration provides the picking point and the placing point. And the loss function here is the cross-entropy loss function, because the discrete distribution where each class is considered to be a pixel in the image. All right, so here is the policy in action on some qualitative example for the bag manipulation task. And this is the normal transporter. So we're just applying it on the newer task that we develop in our simulator that involve inserting one or two items in the bag after we open it and then putting it into a target zone. We've also shown results with goal conditioning. So in this test time example, the robot is successfully putting the item into the yellow bag instead of the blue distractor bag. So in the paper, we show quantitative results across all the 12 tasks in the benchmark, where we compare either the transporter or the goal condition variant, whichever one is appropriate. We compare those with methods that use ground truth, pose, and vertex information. And we find that the transporter-based approach is orders of magnitude more sample efficient than those other approaches that don't use images but use ground truth information about poses. But there are some obvious limitations. So one here, which also applies to the prior work, is that the course pick and place policy cannot react in real time. So you see what's happening here. When it tried to pull the bag upward, the cube falls out. So the right thing that we want the robot to do is stop whatever you're doing, put the bag back down, and then try again. So it'd be good to see if we can address this in future work. All right, so to recap some of the prior works, we've shown some promising results for training picking and placing policy for deformable manipulation, which include model-free learning, model-based learning from the algorithm perspective. From the architectural perspective, we've shown that transporter networks provide a strong prior for sample efficiency and rearrangement. We've shown physical experiment and simulation experiment using a wide range of deformables. And in future work, we'll address the limitation with the picking and placing action idea. And there's always room to improve in terms of sample efficiency and generalization to a wider range of configuration, objects, and so on. So in this next section, what I want to talk about now is a slightly broader technique for using curriculum learning to accelerate learning more generally. So we're going to discuss the work that we've done in curriculum learning for Atari and MuJoCo environments, And then we'll see later how we might be able to tie this with deformable manipulation in future work. So here's some intuition, and an effective teaching method seems like it should choose examples that are within a student's comfort zone. So these examples will not be too difficult, but they're also not going to be too easy that the student doesn't really learn from it, anything. So psychologists have formalized this as zone of proximal development theory. There's a very fundamentally close relation to curriculum learning because in many cases in machine learning context, curriculum learning is about trying to arrange samples in order from like easy to hard to accelerate the learning. And in the context of deep reinforcement learning, one of my favorite examples of curriculum learning is embodied in the GIF from the reverse curriculum generation for reinforcement learning paper, where the goal is to insert this item onto a peg. And with reinforcement learning with random exploration, it's difficult to solve this, but if the starting state is sampled really close to the final state, then reinforcement learning will be able to do this pretty easily. And then we can sample starting state further and further away until the robot is able to do it anywhere. So yeah, again, that's some background and context on curriculum learning. And what we did specifically is we investigated ZPD learning for off-policy deep reinforcement learning context. We have some results for Atari environment as well as MuJoCo later. So we're in the discrete control environment. We're using double DQN as the base agent for the student and the teacher agent. So here, the question that we pose is, if we have n teachers, which one should the student use? And here, the teachers are providing off-policy samples. So the samples are the usual state, action, reward, and so on that's used in many reinforcement learning algorithms. And again, the intuition is that at different points in the student learning progress, different teachers might be better at different times. So in our context with Atari, here's how we generated the teacher. So the first thing that we did is, if you imagine the plot here that shows the training curve for a breakout, which is a common environment in Atari, we can train a teacher and then the curve will look like, the reward curve will look something like this. What we can do is we can extract teachers from snapshots at regular intervals from the training history. So that means the first teacher, T1, might be extracted from a point very early in training. So it won't be that much better than a random policy, but it will be an option for a teacher. Then later we can extract a later snapshot that's a little bit further ahead, and so on until we get to n teachers sampled from snapshot at regular interval, so that the later teachers are considered more advanced than the earlier ones. So that's how we get the teachers, and each of the teachers will provide a data set of off-policy samples. So each teacher is associated with a data set. Here's the algorithm framework that we're pursuing. So the input, again, is the set of data from the teacher snapshot from the prior slide. The key thing that we're proposing here is what we call f-select. So that's a selection function that, given the current student, will pick what we call a ZPD teacher at a given time, right? And the strategy that we're proposing to use is called what we call a K ahead. And what this does is pretty simple. It takes the current student performance based on reward, it matches it according to some teacher, the closest teacher performance, and then given that, we'll just advance the teacher index by K. And so with high probability, what this will do is, this will pick a ZPD teacher that's a little bit further ahead from the current student in terms of performance, but not too far ahead. So now that we've picked a teacher, we have the teacher sample. We also have online samples from the current student. And From there, we can combine both of the data sets just by sampling from both replay buffer and combining the data. And then we do a usual gradient update. So we're actually going to use a DQFD dial law function. So this is deep Q learning with demonstration, where the demonstration are from the teacher. So yeah, that's the algorithm framework that we're following in this work. So we have some results for experiments on 9 different Atari environments, where for each teacher, we really have 23 teachers from sampling snapshots from the teacher training run. We evaluate based on the student performance over this entire training period and the last 100 episodes. And we find that always choosing the best teacher usually it isn't the optimal choice. Like empirically, the better decisions are like picking a teacher that when we match to a student, we advance 5 or 10 steps ahead in the indexing order. Or we can even pick a teacher, a random teacher that's ahead of the student's performance. So why might this work? So the intuition again is, well, maybe with the teacher, we're getting a different teacher each time, so we avoid overfitting to a specific teacher. But one piece of intuition that I find quite illuminating is that if you look at the video, it showed breakout, and it showed the point in time when the teacher is like had almost cleared the board, but is like just unable to get those like last few annoying bricks. And this kind of data is going to dominate the state distribution of advanced teachers. But from a beginning student perspective, the student really had to know how to get to the state in the first place. And that might not be possible just from a beginning student. We have also shown some similar analysis in MuJoCo environment, where now we're in continuous control. So the base algorithm that we use is twin delayed DDPG. So here, the teachers, we're going to run them using normal TD3 on an environment like HapCheetah. That gives a set of data from the teacher log training history. Okay, now that we have all this data, we have students. The students are also TD3 agents. So what's the ideal way that they can learn in an entirely offline fashion from that teacher data? One option, and the most straightforward one, is we provide the entire buffer available to the student agent and say, when it's sampling data, it can sample from any time index. So that can work, at least in this case, it's able to learn eventually, but we've also shown that if we restrict the number of samples available so that near the beginning of training, the student is not able to sample from later time indices in the teacher training history, that results in significantly faster learning. So these are results that we're actively exploring right now in the context of curriculum learning for MuJoCo environment. Okay, so now that we've discussed some curriculum learning, let's see how we might be able to use it in the context of extending some of the deformable manipulation work that we've done and that we hope to do going forward. Okay, so one project that I'm very excited about is trying to get a bimanual robot to handle and insert arbitrary items in a bag. And the reason for a bimanual is that it's a lot easier and a lot more natural to use 2 manipulators instead of 1 for a task like bag manipulation. And yeah, again, the success here is basically if the robot lifts the bag or the items in it. So what are the options for curriculum learning? So some options include going from like an easy to hard item. So some items might be easy to insert, like they might be a cube, a small cube. Some items might be harder, they might be very irregularly shaped, so they have to be inserted at an appropriate angle and so on. Another idea of a curriculum would be trying to train a robot that can first put in 1 item in a bag. Once it's able to do that, can put 2 items in. if it's able to do that, can it put 3 items in? And there are extra challenges that come with putting in multiple items in a bag. So if you imagine this example where the robot is putting in 1 and then 2 items naively, so like putting it near the center of the bag opening, the second item goes on top of the first. So when the robot tries to lift the bag up, the second item falls out. In contrast, if we have a more clever policy, maybe one that has picking, placing, and pushing action, the pushing can make it easier for the next item to be inserted. So now the first item is sort of effectively holding the bag and making it a little wider for the second item so that when the bag is pulled up, it contains the item. So again, at a high level, the idea here would be to try to define some kind of curriculum that can make it easier to accelerate training so that the robot can continually insert more and more items in these bags. So we can do this with, like, for example, 2 UR5 arms in simulation. We can also use a simulated Yumi arm, which could be beneficial if in case we want to do experiment with the physical Yumi robot that we have in our lab. So other future work ideas that I'm very interested in pursuing are, first, I'm very interested in multimodal sensing. So I worked a lot in vision-based policies for robotics, but other senses like using touch sensing could be very useful, and especially when vision is limited or unavailable. So if you remember back when we used to travel, we would use something called suitcases. And suitcases tend to have like many items stacked on top of each other, like but layers and layers of clothing. So if a robot has to like insert or retrieve items that are buried deep within some suitcase, typically that might be a case when maybe vision won't help too much, but maybe touch is going to be very useful. Other things that I'm interested in exploring are better gripper design, better primitives. So for example, we can have like sideways gripping instead of naive top-down grasping that I've mostly done. Other ideas include using newer simulators such as SoftGym, and this supports liquid, so maybe we can eventually use it to train physical robots to handle liquids and sauces. Other ideas include dynamic manipulation, so this might involve tossing items or tossing cables. So the broader theme that I hope you get out of this talk is I'm very interested in getting robots to manipulate the novel, challenging objects in these unstructured settings. So that's the grand challenge of robotics that I hope to pursue in the coming years. And I'm very humbled by how far we have to go, but I'm very optimistic that we as a community will make a lot of progress in the next going forward. Okay, so now we have what I hope will be a very fun section on acknowledging and thanking many of the people who have helped me along my journey. So I think number one, typically most people will start with a discussion of their advisor, thanking them for their, thanking them. And I think this is definitely the case for me. So I definitely would not have been able to do a PhD on my own, and I definitely needed some help getting started with research. And I was also a very unusual student as well. So if there's nothing else that I want my advisors to know, I want to thank them for their patience, technical guidance, and support throughout the years. So John is, very briefly, John is a very good at like any area of CS. So he's a jack of all trades kind of person. And Ken is he's like the leader in robot manipulation, and he helped me enter this field. And so when I was looking at their PhD thesis, like trying to understand how to write a thesis like them, I looked at their acknowledgement section, and I saw that they both acknowledge each other in their dissertation from like 35 years ago. So on my end, I think I'm trying to think about how I would write an acknowledgement section, and it would be the length of a book. But yeah, maybe I'll just do that. So yeah, thank you very much. And For those who helped me out at the very beginning, the three people who I spoke to a lot when I first came to Berkeley are BA, Hallyu, and Pablo. And BA is probably the person who I've spoken to the most in the first half of my PhD. And when he graduated, he left me this note. And the note said, if you can read it carefully, it said, don't just work harder, but also live better and enjoy your life. Good luck. So I think I definitely enjoyed the work I was doing. I definitely did work hard, but I also thought hopefully I lived better. And so, oh yeah, and also I was recently, communicating with him on WeChat, and his last message here said, yeah, thank you. So if you know BA, he said hi. Um, and yeah, there were a lot of people in Ken's lab who helped me adjust to Berkeley. So Jeff and Florian were the two that I spoke to the first who helped me publish a paper, and they provided a lot of technical expertise. Same thing happened for the students I met later, including Michael, Sanjay, and the postdoc Roy, and they taught me a lot about research, and they were patient with me when I pestered them with questions. And yeah, thank you very much, and go Ambi Robotic. Yeah, and other people who provided recent, advice, expertise include, the people shown here, where they provided technical expertise. And one thing, especially with John's lab, is very diverse in terms of research. So there are people who do vision, NLP, explainable AI, HCI, and even research with protein. So I've gotten a good sense, a brief sense of what's happening in those other areas. I've also had discussions about, research life, technology, and geopolitics. So if you're listed on this slide, you know who you are when I say these things. And the last slide is thanking a bunch of my more recent collaborators. So yeah, upper left are very frequent collaborators. Upper right are talented undergrads. Lower left are some Google mentors, and lower right are some postdocs and other mentors. So yep, I think that's it. And that's the end of my talk. So I hope you enjoyed it. And yeah, if you have anything you want to bring up, we can happy to discuss. So